Right, I'd like to talk about the direct comparison test, limit comparison test, DCT, LCT, with these integrals a little bit more. This is an area that it's very abstract, it's very creative, and just creating a function to compare something to, and very different for those reasons. So I just want to explain things a little bit more, try to get you to think about things in a slightly different way, provide a couple more examples. So let's start by talking about the direct comparison test. So remember what the direct comparison test tells us. I'm just kind of abbreviating here. I'm not doing a formal definition. But if we have two functions and we know that one function is always bigger than another function, they're both greater than zero, well, then we can use this to tell us some things about their integrals. So if the integral from c to infinity, and I'm using c here just because it really doesn't matter what number we start at. It could be any point, any set point. C just needs to be a constant, can't be negative infinity. But if we start at any value and head off to infinity, of our function g of x dx, if that integral converges, then the integral of from c to infinity of f of x dx has to converge as well. If the larger thing rather is converging, the smaller thing has to converge too. If the integral from c to infinity of f of x dx diverges, if the smaller thing is divergent, then the integral from c to infinity of g of x, the larger thing, also diverges. So again, not the formal full write out, but just kind of a quick snapshot of what's going on. Limit comparison test works a little bit differently. It doesn't care about the comparison, the direct comparisons of how f and g look to one another. What it looks at is the limit of the two. So we take the limit as x goes to infinity, and it does not matter which one we put on top. We just want the limit of the two functions, so the ratio of the two. That equals L, and L is between 0 and infinity, non-inclusive, meaning we can't equal 0, we can't equal infinity. Then the integral from c to infinity of f of x dx and the integral from c to infinity of g of x dx either both converge or both diverge. And once again, just like on the left-hand side, f and g have to be greater than 0. That is a requirement for both of these. A couple of things I want to point out. One, in both cases, we are looking at the integrals as we head to infinity. We do have to be headed to infinity. So this does not work. These comparison tests don't directly relate to when we have asymptotes, when we have undefined points within the interval. We also need to have some continuous space on these intervals. So we cannot have a disconnect between c and infinity. We have to have a continuous function f and g in these intervals. But what I'm realizing here is I've got to know something about that other function I'm choosing to compare to. So it doesn't matter whether you call the original function f or g. I mean, it does in terms of when we're using our direct comparison, we're going to have to make that choice. But generally speaking, f and g, one is our original function and one is the function we're choosing to compare to. We want to make sure we're choosing a function to compare to that we know what it does, or we can easily figure out what it does. We won't always necessarily know directly, but we can easily figure out what it does. Otherwise, we've just compared it to something and we're still not getting anywhere. So we want to think about how we can simplify that original function in a meaningful way that allows me to speak about convergence divergence. It's kind of the general idea. Now, especially with the direct comparison test, because we have specific rules here, because we can't just say, oh, if f of x converges, then g of x always converges. That's not true. Because the inequality matters, it is useful to go into the problem with a little bit of knowledge about whether the function is going to converge or diverge. Because if I believe the original function is going to converge, well, I wouldn't want to find something smaller than it to also converge, because that tells me nothing about the larger function. Conversely, if the original function, if I think it's going to diverge, I wouldn't want to choose a larger function still that's also divergent. So going into the problem, if we're going to use a direct comparison test, a limit comparison test, I want to generally have an idea of what it's going to look like. Now, how can we do that, right? That is a challenge because we are creating something brand new and at the same time trying to guess at what the original function is going to do. There are some obvious cases. It's x, and we're going from 1 to infinity. we know what this thing looks like, right? It looks like that. We're going from one, so we're going here. We're looking at all this area. An integral is just an area under a curve. Well, clearly these areas continue to grow and grow and grow, right? Over this much space, we have, from here to here, we have this much space. If we go a little farther, we add a lot more space to it. We continue to add space as we go along. So this is clearly a divergent integral. So one of the things that we need to really be looking for is the function needs to be collapsing to zero. If it's not, we're just going to continue to add space in. Even if I had a constant function, 1 to infinity of, let's just say, 2 dx. Well, that's an infinite rectangle. If I stop at, let's say this is 100, I get an area of 200. But then if I go out to 200, I get an area of 400. And so we're just tacking on more and more every single time we go a little bit further. This is never going to converge. This is also going to diverge. I'll point out both of these integrals very simple antiderivatives. So we could find those very simply by, we want to use that replacement of, call it A, B, C, whatever, use those limit statements. Kind of skipping the step. We should really do that back here in the integral. But we should use those limit statements. It's very easy to show using the direct computation of the integral that these things diverge. So then we run into the case as well, okay, now it's starting to converge down to zero. So we can see that those areas are getting smaller and smaller, right? We can see those heights are getting smaller and smaller, but we are still adding more and more rectangles. So for instance, here I have a little bit of space. If I go a little bit further, I'm adding a little bit more space. We see that these rectangles are getting smaller and smaller. And my hand's a little shaky. These rectangles should be getting smaller and smaller. They're closer and closer to the x-axis. But because we continue to go out infinitely from left to right, we are adding infinitely many more rectangles. So the question becomes, does this collapse? Does the height of the rectangle become so small that even though we continue to add widths, it's converging towards a single number? This area is converging towards a single number. And so we've already talked about the two, the p cases, the x to the p dx. If p is greater than 1, it converges. And if p is less than 1, it diverges. So picking out two cases in particular, if we look at the integral from 1 to infinity of 1 over x dx, that would diverge. And the integral from 1 to infinity of 1 over x squared dx, that would converge. Both of these pictures are going to look very similar. If we think about what a rational function looks like, it looks like something like this in the first quadrant, and we're going from 1 onwards. So that area is actually divergent, meaning we cannot get a set out value. We're continuing to add more and more terms, so we're never going to have a largest value that we're approaching. On the second one, however, because it collapses in a little bit faster, again, shaky hand, apologies, because it's collapsing in a little bit faster, we are getting a convergent area. And so one of the things I'm always looking to see is, how quickly is that denominator growing? Is that going to collapse my function in quick enough? Or is it going to continue to expand? So let's take some examples of this. Let's take the integral from pi to infinity of 1 plus sine of x over x squared dx. I'm just going to be determining if these things converge or diverge. I'm not going to be finding the actual area under the curve or the actual value of the integral, just determining if it's convergent or divergent. So if I look at this, I'm trying to get an immediate reaction of whether I think it's going to converge or diverge. What I notice is at the top, we have a 1 plus sine. That's hanging around values between 0 and 2. Sine, most it's ever going to be is 1, least is -1. On the bottom, we have that x squared. That is going to get very, very large as x goes to infinity. So the top's kind of really not going anywhere. The bottom is driving this thing to 0. And that's what we were just talking about, that need to eventually collapse inward. Now, we could still have one of these two general pictures. It could be collapsing in too slowly, or it could be approaching our 0 quick enough. It could be approaching the y equals 0 quick enough to where the function is going to have that finite area, a convergent value for our integral. And so then the question becomes, which of the two is it? Well, let's base it off our previous knowledge. I'm really looking to see, is it collapsing as quick as that 1 over x, or maybe not quite as fast? Well, the numerator, like we've already talked about, is just a set value between 0 and 2. It's relatively stable. It's more or less constant. It's not 100% constant, but it's a relatively constant value between 0 and 2. The denominator, we see that x squared. So right away, this is drawing me into the p equals 2 case, which I would believe it would converge. So I'm going into this problem trying to with the thought that it converges. There are going to be times that I get that wrong. and I've been doing this stuff for a long time, I still will occasionally guess the wrong way. And usually as you're trying to set up the direct comparison and limit comparison test and you're finding that certain things aren't working, that's going to kind of lead you to reevaluate your initial belief. But I want to go in with kind of a baseline assumption. I think this is going to converge. Sines, cosines, trig functions, very, very challenging to take their limits because they continue to oscillate. So I want to avoid a limit comparison. So that's going to lead me to believe I want to use a direct comparison. First thing to note, is this function greater than 0? Yes, it is. Sine, the smallest it can be, is -1. Technically, it is equal to 0 at points. I'll live with that. It is equal to -1 at points, but it's going to remain positive, and that's kind of the key. We're using that 0 as our lower bound. On the other end, we need something that is going to be larger that we know converges. Because going back all the way to the top, that rule that we started with, in order to state that this thing converges, we need a larger thing that also converges. So I don't want to really change too much at a time. I'm only going to mess with the numerator to denominator at a time. Just trying to change too many pieces at once, it gets too confusing. So I'm going to look at one component at a time. The x squared in the denominator really isn't a problem. That part of it we believe is convergent. If we just had the function 1 over x squared, that'd be an easy integral. We'd have something else there. We have that sign. So can we think of a max value for that sign? Yeah, we already said it was 1. So why don't I just say 3 up here? Because at most we could have 1 plus 1, 2. I guarantee 3 is bigger than that. So I'm confident that the function I've chosen is bigger than my original function. So now if we were to think about the integral, and this thing is going from pi to infinity, remember it really doesn't matter. 0 would be an undefined point. We've surpassed that. We've gone past that. So if I look at this integral, we can say this converges. And we know that because our p is greater than 1. It's not exactly the p rule. We can always just pull that 3 to the front. There we have that exact 1 over x to the p case. And so because the integral from pi to infinity of 3 over x squared dx converges, and because we know that 1 plus sine x over x squared, we know the integral of the 1 plus sine x over x squared from pi to infinity dx also must converge by the direct comparison test. So I'm going to be looking at inequality. We need to convince ourselves that is true. And generally speaking, if something is obvious to me or obvious to you, I think it's going to be obvious to me. Don't try to make huge assumptions, right? So I wouldn't want to say, just making something crazy up, that this is less than the secant of x times the cosine of x times the tangent of x plus x cubed over x to the fifth. I have no idea if this is true or not. I'd have to think about it. I don't want to think about it, but that's kind of thing. Don't jump to that final answer. Build your way up. Now, of course, this right-hand function would give us, we wouldn't know how to do its integral. So that's absolutely meaningless. But make sure when you're using your inequality statements, you are stating inequalities that you know to be true and that it is immediately obvious. And if you need to show a couple steps, show a couple steps. We'll see examples of that as we get through. So I've shown that inequality. I've stated that the thing I'm comparing to either converges or diverges. This case is very simple because it's just a p case. And then we stated the result and how we got to that result. That is the direct comparison test. That is a C. All right, let's take another example. Let's take the integral from 1 to infinity of 1 over e to the x plus 2 to the x dx. So the previous one was a really good direct comparison because we had that function cosine, which is not easy to take its limit. When are the limit comparison tests easier? Well, I already did a previous example in a video in class where we had polynomials. Polynomials really easy to take their limits. It's easy to manipulate limits in those cases. But if we have functions that we don't know what their limits are, if we have multiple functions, those can be challenging to use a limit comparison test. So here I see an e to the x plus 2 to the x, same type of function, but what would I need to create to find the limit here? That's challenging because we have multiple types of functions, multiple bases. So again, I'm thinking about direct comparison tests, and for that reason, I really need to go in with a baseline assumption. And 1 over e to the x plus 2 to the x, that denominator is getting huge very, very quickly. I believe this is going to once again converge because that denominator is growing so fast, right? It's not comparable to the 1 over x. It's much, much larger. E to the x much larger than even an x squared. So I'm going to look for my direct comparison test. I know this thing is greater than 0. And I'd really, in order to do that integral, the thing that's making it challenging is the fact we have two different components in the denominator. I'd love to be able to drop one or replace one. Well, if we make our denominator smaller, we make the fraction as a whole bigger. Think about flipping that over. If I gave you the statement e to the x plus 2 to the x and the statement e to the x, I think it's very clear to see 2 to the x, not 2 times x, that the left-hand side is bigger because there's more stuff there. The second you take a reciprocal, you flip over that fraction, you've got to flip over your inequality sign. And so that's why that is true. Anytime you make your denominator smaller, you make the fraction as a whole bigger. If you make your denominator bigger, you make the fraction as a whole smaller. So I have a true inequality. I know it's greater than 0. I'm going to integrate 1 to infinity of 1 over e to the x dx. Now, this is one that we don't have a p rule for, right? It's not that x to the p case. And so we are actually going to have to do this integral. But the nice thing, it's a relatively simple integral. I start by replacing the infinity with some variable, we'll call it a, go from 1 to a. And I'm going to rewrite that e to the x in the denominator as e to the negative x dx. So my antiderivative would be limit as a goes to, that should be an infinity, not an a, of negative e to the negative x. And we're going to integrate that from 1 to a. So I'm going to plug in limit as a goes to infinity of negative e to the negative a minus a negative turns into a positive e to the negative 1. Well, e to the negative 1 is just a set value. So if we just had that, it would be convergent. The question is, what's going on with this piece? So I think a lot of times it is easier to see exponents, those negative exponents, written as a fraction. Remember, it's just flipping it over. We did the same thing with the e to the negative 1. That one we already said 1 over e to the 1 is convergent. So if we have negative 1 over e to the a, well, as a gets huge, the denominator is getting huge. 1 over 10, 1 over 100, 1 over a million, 1 over a billion. That fraction right there is going to 0. And so when we take our limit, we're left with 1 over e. So even though we started with an integral that we did not know if it converged or diverged from the start, we thought it converged. We didn't know it for certain. We had to show it this time. We actually were able to take something much more complex that I don't know how to take its integral. I don't know how to find that antiderivative. I was able to compare it to something very, very simple that was easy to find its antiderivative, so we could show that it does in fact converge. And now I'm going to write up what my result is. So because the integral from 1 to infinity of 1 over e to the x dx converges, and 0 is less than 1 over e to the x plus 2 to the x, which is less than 1 over e to the x, then by direct comparison test, the integral from 1 to infinity of 1 over e to the x plus 2 to the x dx also converges. Now I put it up here just so we can see the problem all at once. Better form, I think, just keep going down your page. Don't try and squeeze things in here and there. Just keep going down. But just because I'm trying to show it all on one screen, that's what we got going on. Okay. Let's take one last example. So I haven't done anything with the limit comparison test yet. Let's take x dx over the square root of x to the 4th minus 1. So limit comparison, the direct we've seen its uses when we have things that we don't know how to take the limits of, or if we have those multiple functions. The challenge with multiple functions, you could see it side to side like we done in the last one, or top and bottom. In order to get to a limit, when we take that f over g, in order to get that limit, we need those functions to cancel in some ways, or be able to use L'Hopital's in order to get those functions to cancel. And if we have different functions, that just is relatively challenging. They're not going to cancel quite so easy. Versus when we have polynomials or just powers, even with the square root here, it hopefully will be a little bit easier for me to use a limit comparison. I do think on this one, you could actually use a direct comparison too. So there's multiple ways of doing this. So I'm actually going to think about it almost through a direct comparison lens first. I'm going to think about whether it's going to converge or diverge, right? And I think this one, if I look at this, I see x in the top. That is obviously growing. X to the 4th in the bottom is growing much faster, but that is sitting under a square root. The 1 is negligible, right? At some point, that 1 just stops to matter as we get out to the infinities. Infinity minus 1 doesn't really matter, especially when we raise that to the 4th. So what's really seeming to matter to me, this isn't formal work, just kind of scratch work, is the x over x to the 4th, which is the same thing as x over x squared. which is the same thing as 1 over x. And we know 1 over x should diverge. So again, just kind of scratch work over here, not really including my formal write-up. But that's the logic going through my head. I think this is comparable to a 1 over x-ish, and I think that should diverge. Well, because I think it's comparable to 1 over x, I could use that in my limit comparison test. I could compare this thing to 1 over x, and we can see what happens. Or, like I said, I think you could use a direct comparison. Didn't think about this before I started talking, so we'll see how quickly it works out. Again, I don't want to change multiple things at once. The thing that's giving me trouble is that -1. If I just drop that -1, I've made the fraction, the denominator, bigger, which makes the thing as a whole smaller. But I could subtract maybe, making that denominator smaller makes this whole bigger. So 1/2 x to the 4th is bigger than 1 as long as x is bigger than 2. In fact, it would be bigger at exactly 2. So that would be true. So we could even drive that smaller if we wanted to, but this is close enough for just ballparking it for a direct comparison test idea. So if that is true, when I start subtracting, if I take x to the 4th and subtract the smaller number, that is giving me a smaller fraction. So that comparison would work. I'd be able to use x over the square root of 1/2 x to the 4th. Because we have a single term down there, we can have the square root of 1/2 and the square root of x to the 4th, which is just x squared. So that would work. But like I said, I'm going to do a limit comparison on this one. So we've already said that I want to compare it to 1 over x. So what I'm going to do, I'm going to take the limit as x goes to infinity of x over the square root of x to the 4th minus 1 over 1 over x. And we can simplify that to be the limit as x goes to infinity of x squared over x to the 4th minus 1. Any number of ways you could simplify this limit. Probably, I think the easiest would be to bring it all under the square root. So I could write this as an x to the 4th over x to the 4th minus 1. And then I can bring the limit inside the square root. If we take the limit inside that square root, we'd get the square root of 1, which is just 1. When we take the limit of the inside, you could divide out the largest power, so x to the 4th. If we divide everything by x to the 4th, we get a 1 here, a 1 here, and that would be an x, 1 over x to the 4th, which is going to 0. That's where I'm getting that 1 from. So because I'm getting 1 for my limit, that tells me that limit test, comparison test is in play. I should also point out 1 over x and x over the square root of x to the 4th minus 1, they are both positive. So conditions for limit comparison test has been met. The integral from 2 to infinity of 1 over x, the thing I chose to compare to right here, is divergent using, because the p is equal to 1, using that p rule. And so we can state that since the limit as x goes to infinity of our original function, the x over the square root of x to the 4th minus 1 over 1 over x is equal to 1, which is between 0 and infinity, the limit comparison test tells us the integral of 2 to infinity of the x over square root of x to the 4th minus 1 dx also converges, since the integral of 2 to infinity of 1 over x squared dx converges. So the more you play with these things, you're going to get a better sense of when things converge and when things diverge. I think that is the first initial hard step, right? On all these problems, I started off by thinking about, okay, do I think it's going to converge? Do I think it's going to diverge? That helps me choose which way I need the inequality to be. I just realized now here, actually, I told you I didn't give the direct comparison a whole lot of thought. I've said everything completely backwards here. We just said that this diverged. Let me stick with what I was just saying. So these should be diverges, and diverges. So because this function diverges, the limit comparison test tells me they do the same. If this one diverged, this one also diverges, this also diverges. So that looks better. So actually, this inequality would be absolutely meaningless because I've just shown the larger thing diverges. So that would be absolutely pointless. So this is where we want to make sure that we know what it's doing going in. I said I thought it was diverging going in. So I don't want it to be bigger than, I would want it to be less than. Actually, a little bit easier. because if I make the denominator bigger as a whole, I've made the fraction smaller. So all that hard work I did to figure out whether I need it to be less than greater than, this is a super simple inequality. This would turn into an x over x squared, which is just 1 over x. So direct comparison test would have been really easy in this one too, right? We didn't have to use limit comparison. But with that direct comparison test, we want to have a good idea of what's going on before we ever start the problem, so we can make sure we get the inequality the right way. And that's a challenge. The more you do of these, the more comfortable you're going to get, right? You're going to get better and better about recognizing, oh, I think this one's going to converge or diverge. Some of them incredibly obvious. If it's not collapsing in towards zero, if the function's not collapsing in towards zero, it's going to diverge. But when it is, you're going to start to pick up on, okay, this feels like the denominator is growing at a quick enough rate, or maybe it doesn't. They're not all incredibly obvious. I would say all three of these were on the easier side because we wanted to start to get a sense of when things are going to converge or diverge. But with that direct comparison test, you've got to have that idea going into it. Limit comparison test, what we saw here is, as long as we know what this one function is doing, we didn't really have to have a great sense of what was going to happen. I chose something I knew diverged. We found that it had a limit value. That was really the most important thing. I needed to have that limit value because that function diverges. Your original does too. Hopefully this helps. If you have questions, let me know.